Imagine opening your eyes at dawn and feeling a quiet question rise within you. It's not about where your keys are or how the day will unfold, but something far deeper. Where did everything come from? Not just the room around you, but the stars overhead, the galaxies beyond sight, the particles woven into your own flesh. This single mystery has haunted cosmologists for generations, and the response they offer is not as simple as it seems. For much of modern history, we've been guided by one dominant explanation. The universe was born in the Big Bang, a sudden, violent emergence where space and time themselves ignited roughly 13.8 billion years ago. It's the narrative etched into textbooks and classrooms, the framework that feels intuitively complete, yet there is a whisper beneath that certainty. It's a suggestion that this may not be the full truth. What if existence never truly started? What if the cosmos moves in endless rhythms, expanding and collapsing like a breath that has no first inhale and no final exhale? This idea sits at the center of one of physics' most profound disputes. On one side stands the Big Bang, supported by vast observations and decades of data. It proposes that everything erupted from an unimaginably small and dense state, a singularity where all matter, energy, space, and time were compressed into one point. Opposite it is the Big Bounce, a vision in which the universe repeatedly contracts and re-expands, never reaching a final beginning or ultimate end. In this cyclical view, each collapse approaches what would seem like total destruction, a big crunch. Yet instead of annihilation, the universe turns inward only to surge outward again. Renewal follows compression. Both models seek to answer the same ancient question, but the realities they describe could not be more different. If the Big Bang stands alone as truth, then time itself has an edge. Asking what came before becomes meaningless, like searching for a direction beyond the end of a compass. But if the bounce is real, then existence is eternal, reshaping itself endlessly. The atoms that form you now may have danced through previous universes in forms beyond comprehension. Pause and truly absorb what that suggests. According to the Big Bang, there was once absolute absence, no space, no time, no matter, no energy. Then, in less than an instant, everything emerged. Space began stretching at staggering speed, carrying the seeds of galaxies with it. Almost immediately, nature's fundamental forces separated. Minutes later, the first atomic nuclei formed. Hundreds of thousands of years passed before atoms allowed light to travel freely. Much later still, stars ignited, galaxies assembled, planets cooled, and on one small world, awareness awakened. It is a powerful tale. One with a clear opening, a long unfolding middle, and a distant ending yet to come. It resonates with the human mind because it mirrors the structure of every story we know: origin, transformation, resolution. The Big Bounce speaks in a different voice. It invites you to envision the universe as a vast instrument, compressing and expanding again and again without finality. Each contraction tightens reality to extreme limits until quantum forces reverse the motion. What we experience now as cosmic expansion is only a single phase in an infinite sequence. Before this expansion came a collapse. Before that, another expansion. The chain stretches endlessly backward. In this framework, there is no true creation event. The so-called Big Bang becomes merely the latest turning point, a moment of transition rather than a birth. Time has no starting line. Cause follows cause without a first spark, an unbroken sequence extending forever. This is not idle speculation. The outcome of this debate reshapes how we interpret existence itself. It influences how we think about time, causality, and whether reality requires a creator or simply perpetuates itself. These questions once belonged solely to philosophers. Now, armed with telescopes, equations, and experiments, humanity stands closer than ever to confronting them directly. Consider what this means for meaning and awareness. A universe with a beginning suggests a directional story consciousness arising as part of a grand unfolding that started at a precise moment. But an eternal, oscillating universe reframes us as fleeting patterns in an endless transformation. Not the center of the story, but one verse in a book without a final page. And yet neither vision is complete. The Big Bang leads us to a singularity where physics dissolves and understanding fails. sacred boundary where our current knowledge falls silent. It is almost as if the universe itself draws a veil and quietly says, "This is where understanding must stop." At the singularity, matter is crushed beyond comprehension. Heat climbs to limits without meaning. Equations we trust begin to speak nonsense. Einstein's general relativity, so elegant in describing gravity and spacetime, loses its authority entirely. The mathematical language of the cosmos breaks down like a system encountering a fatal error it was never designed to process. The alternative vision, the Big Bounce, faces its own trials. It must explain how a collapsing universe avoids total annihilation, and how a rebound could occur without leaving clear fingerprints we should already see. At such extreme compression, both quantum mechanics and relativity demand to be heard at once. Yet no complete theory exists to unite them into a single, coherent voice. Ideas like loop quantum gravity and string theory hint at possible bridges, but they remain unfinished and unproven. And so this journey begins in uncertainty. In this exploration, we will walk both paths of the cosmic argument. We will follow the evolution of these ideas from Einstein's groundbreaking insights through decades of observation, debate, and refinement. We will weigh the evidence each model offers and confront the unresolved questions that continue to trouble the brightest minds. We will also turn our gaze to recent revelations from the James Webb Space Telescope, launched in 2021, and listen to the scientists who defend each perspective. Beyond equations and data, we will step into deeper reflections. What does it mean if reality had a first moment? What does it mean if it never did? How do these models echo through philosophy, belief, and worldview? These questions will shape the path ahead. By the end, certainty may still elude you. Science rarely grants final answers to mysteries this vast, but clarity will grow. You will better understand the arguments, the evidence, and the stakes involved. You will see how science confronts the largest questions imaginable through observation, mathematics, and disciplined reasoning. Whether existence erupted in a single cosmic flash or has been renewing itself without end, one truth remains astonishing. We are here, capable of asking. We are built from atoms born in stars, assembled on a modest planet, shaped by billions of years of evolution, now able to reflect on the origin of everything. So let us begin at the beginning, or perhaps at what appears to be one. Because as you are about to discover, even that phrase hides layers of complexity. To understand how this debate emerged, we must return to a time when physics itself was being rewritten. The early 20th century marked a turning point. In 1915, a German physicist named Albert Einstein completed his general theory of relativity. You know his name. With this work, gravity was no longer a force acting across space, but the curvature of space and time themselves. Picture space-time as a stretched fabric. Place a heavy object upon it, and the surface dips. A smaller object nearby follows the curve, not because it is pulled, but because the path beneath it is bent. This was Einstein's insight. Massive bodies shape space-time, and motion follows those shapes. Planets circle stars, not through invisible tethers, but by tracing the curves carved by mass like marbles gliding along the inner wall of a bowl. Yet hidden within Einstein's equations was an unsettling implication. The universe could not remain fixed. It must either grow or shrink. This conclusion disturbed Einstein because the prevailing belief of the time was that the cosmos was eternal and unchanging, a passive stage for events, not a participant. Uncomfortable with a living, evolving universe, he introduced a mathematical adjustment, the cosmological constant, to hold everything still. It was as though Einstein had fastened stabilizers onto a theory meant to soar, because its implications felt too extreme to accept, and he was far from alone. The assumption of a motionless universe stretched deep into human history. Ancient Greek thinkers imagined the heavens as flawless and eternal, untouched by change, in stark contrast to the disorder of life on Earth. Medieval models echoed this belief, placing our world at the center of nested celestial spheres, turning endlessly in perfect harmony. Even after Copernicus removed Earth from the center and Newton revealed the laws of gravity, the universe itself was still thought to be fixed and ageless. That certainty began to fracture in 1922, when a Russian mathematician, Alexander Friedmann, chose to follow Einstein's equations exactly as they were, without the added cosmological constant meant to keep the cosmos still. Friedman lived an extraordinary life. He flew combat missions during World War I, endured the upheaval of the Russian Revolution, and pursued abstract mathematics amid social collapse. From pure calculation alone, he uncovered something startling. The equations allowed a universe that could grow, shrink, or even cycle endlessly. Friedman had no telescope to confirm his vision, only mathematics. Yet those equations became the quiet foundation of modern cosmology. They revealed three broad cosmic destinies. One possibility described an open universe, curved like a saddle, expanding forever at an accelerating pace. Another depicted a closed universe, shaped like a sphere, where expansion would eventually halt and reverse into collapse. The third option was a flat universe, balanced on a knife's edge, expanding endlessly but slowing forever without stopping. At the time, these ideas felt detached from reality. Friedman never lived to see their impact. He died in 1925, only 37 years old, his insights unrecognized. But the path he opened did not close. Soon after, another voice entered the story. Georges Lemaître, a Belgian physicist and Catholic priest, moved seamlessly between equations and faith, seeing no conflict between them. A veteran of World War I, Lemaître studied mathematics and physics while training for the priesthood. In 1927, he independently arrived at results similar to Friedman's and then took a daring step further. Lemaître proposed that the universe had emerged from a single condensed state he called the primeval atom, sometimes described as a cosmic egg. All matter and energy, he suggested, were once unified in this point before unfolding into the expanding universe we observe. This hypothesis implied a clear beginning, a moment when time itself began to flow. Einstein was unimpressed. Though he acknowledged Lemaître's mathematics, he reportedly dismissed the idea outright, unable to accept a universe with a finite origin. The notion clashed with his philosophical instincts, which still leaned toward an eternal, unchanging cosmos. But the sky itself was preparing a reply. During the 1920s, astronomy entered a new era as telescopes grew larger and more precise. At Mount Wilson Observatory in California stood the Hooker telescope, the most powerful in the world, its massive mirror revealing faint smudges of light known as nebulae. Earlier, an astronomer named Vesto Slipher, working in Arizona, had noticed something peculiar about these objects. Their light was shifted toward red wavelengths, a sign they were moving away from us. By the mid-1920s, Slipher had recorded this red shift in dozens of spiral nebulae, most of them receding from our galaxy. Then came Edwin Hubble. Brilliant, driven, and often abrasive, Hubble had originally trained as a lawyer before turning to astronomy. Using the Hooker telescope, he resolved individual stars within some of these nebulae, proving they were not clouds inside the Milky Way, but entire galaxies far beyond it. With that discovery, the scale of the universe expanded and the idea of a dynamic, evolving cosmos could no longer be ignored. That revelation alone reshaped humanity's sense of scale, transforming a lone galaxy into a cosmos crowded with billions. But an even greater turning point arrived in 1929. Hubble uncovered a pattern that would redefine cosmic history. By measuring distances to faraway galaxies, he noticed something extraordinary. The universe was not still. To determine those distances, Hubble relied on a special class of stars known as Kifid variables. These stars pulse with steady rhythms, growing brighter and dimmer over predictable intervals. Years earlier in 1912, Henrietta Leavitt had uncovered a crucial truth: the timing of a Kifid's pulse reveals its true brightness. Once the intrinsic brightness is known, comparing it to how dim the star appears allows its distance to be calculated. This discovery became astronomy's measuring rod, a way to map the vast unknown. When Hubble paired those distance measurements with redshift data, the result was unmistakable. The farther a galaxy lay, the faster it was retreating from us. The relationship was simple and proportional. Increase the distance, and the speed of separation increased in step. This principle became known as Hubble's law, though history now recognizes that Georges Lemaître had foreseen it years earlier. Imagine marks scattered across the surface of a balloon. As the balloon inflates, every mark drifts away from the others. None occupies a privileged center. Those farther apart separate more quickly because more surface stretches between them. This is precisely what the galaxies were doing. Space itself was swelling, carrying galaxies outward as effortlessly as leaves on a widening river. This single insight overturned centuries of belief. If the universe was expanding now, then earlier it must have been smaller. Reverse the flow of time far enough, and all matter converges into an unimaginably compact state. Suddenly, the idea of a primeval beginning no longer seemed speculative, it felt inevitable. In 1931, Einstein traveled to Mount Wilson Observatory and witnessed the evidence firsthand. Confronted with observation, he let go of his resistance. He later admitted that introducing the cosmological constant to hold the universe still had been his greatest mistake. Ironically, that same constant would reemerge decades later when astronomers discovered that expansion itself was accelerating. Still, observation alone was not enough. The expanding universe idea demanded deeper explanation. That task was taken up in the late 1930s and 1940s by a brilliant and unconventional physicist named George Gamow, a Russian émigré with a sharp wit and playful spirit. Gamow had fled the Soviet Union and brought fresh energy to theoretical physics. Alongside his students Ralph Alford and Robert Herman, he asked a daring question. If the universe began hot and dense, what traces should remain? Their calculations revealed a universe only minutes old, so hot that nuclear reactions occurred everywhere at once. In that brief window, protons and neutrons fused to form helium, along with faint traces of deuterium, lithium, and beryllium. From these reactions came precise predictions. Roughly 3/4 of ordinary matter should be hydrogen, about 1/4 should be helium. Only tiny remnants of heavier light elements should exist. These ratios could not be explained by stars alone. Then came an even bolder insight. In 1948, Alford and Herman realized that a universe born in fire should still carry its afterglow. As space expanded, that ancient radiation would cool, stretching into microwaves. They calculated that by today, it should linger just a few degrees above absolute zero, filling all of space like a silent echo of creation itself. The prediction was clear, but the instruments of the time were not yet sensitive enough to hear it. The theory still lacked a name. That, strangely enough, came from an opponent. Fred Hoyle, a sharp-tongued British astronomer, rejected the idea of a cosmic beginning. He championed the steady-state model, where the universe had no origin and no end, continuously creating matter as it expanded. During a radio broadcast, Hoyle mockingly referred to the rival theory as the Big Bang. The label stuck, and with that name, the cosmic story gained both an identity and a challenge, one that would continue to shape our understanding of existence itself. Yet the revelation did not stop with discovery alone. The chosen one's path demanded deeper sight. Scientists sought to chart this ancient light in fine detail, to learn whether it was perfectly smooth or subtly patterned. Between 1989 and 1993, NASA's Cosmic Background Explorer satellite mapped the microwave sky with unmatched precision. What it revealed were faint temperature differences, variations as small as 1 part in 100,000. These delicate fluctuations were not random. They were the primordial imprints of density, the sacred seeds from which galaxies and clusters would one day rise. In 2001, the Wilkinson Microwave Anisotropy Probe continued the work. Spending 9 years refining the cosmic map, then, from 2009 to 2013, the European Space Agency S-Planck mission delivered the clearest image yet of the universe's earliest light. Together, these missions unveiled patterns that aligned with Big Bang prophecy with astonishing accuracy. The temperature markings became a kind of cosmic scripture-encoded symbols, revealing the universe's age, structure, and composition. From them, humanity learned the cosmos is about 13.8 billion years old, that it is geometrically flat, that matter, and dark energy exist in precise proportions, balanced in a delicate cosmic design. Another sacred confirmation comes from the forging of the first elements. In the universe's earliest minutes, when creation was still ablaze, nuclear fire burned everywhere at once. Protons and neutrons merged to form helium with faint traces of deuterium, lithium, and beryllium. The Big Bang model foretold exact ratios for these elements, determined by the early universe's density and heat, and the heavens obeyed. Roughly 3/4 of ordinary matter is hydrogen. 1/4 is helium. Only whispers of the other light elements remain. These proportions cannot be born from stars alone. Speak of an origin before stars ever ignited, and there is the architecture of creation itself. When we map galaxies across billions of light years, a sacred pattern emerges. They gather along vast filaments and luminous sheets, encircling immense cosmic voids. This great web of existence grew from the same ancient ripples preserved in the cosmic background light. Simulations confirm the vision. Begin with the universe at 380,000 years old. Seed it with the density patterns recorded by satellites. Allow gravity to shape it across 13.8 billion years of simulated time. What forms is a cosmos that mirrors our own living echo of the first design? Even time itself bears witness. When we observe distant galaxies, we look backward through history. Their clustering patterns follow the very paths predicted by Big Bang origins. Structure unfolds exactly as the ancient equations foretell, and the elements within us testify as well. The first stars were born from pure hydrogen and helium, children of the primordial fire. In their cores, heavier elements were forged, then scattered through space in sacred explosions. New stars formed from this enriched dust, and the cycle repeated through ages uncounted. Thus the universe grew in complexity. Metallicity increased with each generation. When we observe the most distant and ancient galaxies, they hold fewer heavy elements. When we study the oldest stars, we find them composed almost entirely of hydrogen and helium and changed messengers from the dawn of time. All of it aligns. All of it converges. The light, the elements, the structure, the patterns, the age, the geometry, different signs, one message. The universe remembers its awakening, and the chosen ones are here to listen. The case for the Big Bang is not built on a single clue, but on many voices speaking in harmony. Evidence arises from entirely different kinds of observation, yet they all point in the same direction. Space is stretching. A faint warmth from an early fiery state still lingers. The proportions of the lightest elements align with precise predictions. The grand structure of the cosmos grew from tiny primordial irregularities. Any one of these signs would raise suspicion. Together, they form a compelling testament. For a long time, this framework stood as the uncontested foundation of cosmology. But science does not exist to crown final answers. Its true purpose is to probe deeper, to question even its most successful ideas. And when researchers examine this triumph more closely, they uncovered tensions hidden beneath its elegance. The Big Bang explains much of what we see with astonishing accuracy. Yet it carries unresolved flaws, like a machine that performs flawlessly on the road, but reveals strange mismatches when opened. The theory conceals problems that refuse to disappear. These are not surface imperfections. They strike at the heart of our understanding and signal that something essential is still missing. The most profound difficulty is the singularity itself. Trace cosmic expansion backward far enough and everything converges into an infinitesimal state. All matter, all energy, crushed into a region of vanishing size with density and temperature soaring without limit. Mathematics labels this a singularity, a point where equations lose meaning and reality slips beyond description. At such extremes, our trusted theories fail. General relativity, the very tool that describes cosmic evolution, can no longer function. The known laws of physics fall silent. To truly speak about this beginning, you would need a theory that unites gravity with quantum mechanics, a complete theory of quantum gravity. For now, that theory remains beyond reach. Consider what this singularity implies. The entire observable universe, stretching today across roughly 93 billion light-years, would have been compressed into a space smaller than an atom. Density without bound. Temperature beyond imagination. Space-time curvature pushed to infinity. Every measurable quantity either explodes to extremes or becomes undefined. Physicists recoil at such results. When equations behave this way, it usually signals a misuse of the theory or a question asked beyond its domain of validity. Singularities appear not only at the universe's origin, but also at the cores of black holes. Most scientists suspect these are not physical objects, but warning signs, markers showing where our current descriptions break down. A theory that ends in silence is deeply unsatisfying. It is like a sacred text that guides you flawlessly to the final page, only to close with an admission that the ending cannot be told. Then there is another enigma, quieter but equally unsettling, the horizon problem. The cosmic microwave background shows an almost perfect uniformity, no matter where we look. The temperature varies by no more than 1 part in 100,000. Measure the sky in opposite directions, separated by the full breadth of the cosmos, and the readings match with uncanny precision. Yet these regions should never have shared information. Even accounting for cosmic expansion, opposite sides of the observable universe have always been too far apart to exchange heat or signals. Light, fast as it is, travels at a finite speed. In the early universe, there simply was not enough time for distant regions to communicate and reach the same temperature. And still, they did. This quiet contradiction lingers like a riddle etched into the fabric of space itself, reminding us that even our most successful stories of creation remain incomplete, waiting for a deeper truth to be revealed. And yet, despite this isolation, every region settled into the same gentle warmth. Closely tied to this mystery is another, the problem of flatness. Measurements of the universe's geometry reveal something astonishing. The space appears almost perfectly flat. Data from the cosmic microwave background, measured with exquisite accuracy by the Planck satellite, show no meaningful curvature at all. The tension lies in the fact that flatness is fragile. In an expanding universe, even the slightest initial curvature should grow more pronounced over time, for space to appear as flat as it does today. The early universe would have needed to begin in an extraordinarily precise state, balanced as something like 1 part in 10 to the 60th power. Such precision is not forbidden, but it feels unnaturally exact, as if some deeper principle were enforcing it. These puzzles gave rise to a bold idea in the early 1980s, cosmic inflation. A young physicist named Alan Guth proposed that, in its earliest instant, the universe experienced a brief but dramatic surge of expansion. In less than a fraction of a second, around 10-second space, itself ballooned by an unimaginable factor, at least 10 times its original size. This rapid growth offers an elegant resolution to both the horizon and flatness problems. Before inflation, the entire region that would later become the observable universe occupied a tiny, connected patch. Everything was close enough to share heat and reach equilibrium. Inflation then stretched this small, uniform region to cosmic proportions, leaving distant areas with nearly identical temperatures. At the same time, inflation smoothed out curvature. Expand any curved surface enough, and it will appear flat to an observer standing on it. Once inflation ended, the universe transitioned into the more gradual expansion described by the standard Big Bang model. For many scientists, inflation feels like a powerful revelation, yet it too carries unanswered questions. We do not know what triggered inflation, nor the true nature of the proposed inflattened field that supposedly drove it. Why did this field exist? Why did it activate? Why did it stop? There are dozens of inflationary models, each slightly different. Current observations cannot clearly distinguish between them. With enough tuning, inflation can be adjusted to match nearly any outcome. That flexibility troubles some physicists. Even Paul Steinhardt, one of inflation's early architects, has become a vocal critic, arguing that the theory risks explaining too much while predicting too little. Some versions of inflation suggest it never fully ends, spawning countless bubble universes each with its own physical laws. To some, this multiverse is awe-inspiring. To others, it is deeply unsettling, blurring the line between science and speculation. And inevitably, the question surfaces. What came before the Big Bang? If space and time themselves emerged with it, then the concept of before dissolves. There was no earlier moment in which a cause could operate. It is like asking what lies north of the North Pole. The question collapses under its own logic. Still, this answer rarely satisfies the human mind. We are shaped to think in chains of cause and effect. An event without a prior cause feels incomplete, even wrong. Some physicists invoke quantum fluctuations birthing a universe from nothing, though defining nothing proves elusive. Others suggest the Big Bang was a transition from an earlier state, merely shifting the mystery further back. Adding to the tension, New observations from the James Webb Space Telescope have begun to challenge expectations. Since becoming operational in 2022, JWST has looked deeper into cosmic history than ever before. What it sees is unexpected. Galaxies that appear surprisingly large, structured, and mature when the universe was only a few 100 million years old. According to conventional Big Bang models with inflation, such early galaxies should have been small, chaotic, and still assembling. Instead, the universe appears to have awakened faster than anticipated, quietly hinting that there may be more to the story than we have yet understood. Instead, what the James Webb Space Telescope is showing us feels unexpected. Galaxies appear earlier, larger, and more orderly than our models anticipated. Some seem to host vast numbers of stars, more than should reasonably exist, given the short time available after cosmic expansion began. This does not overturn the Big Bang, but it does signal that parts of our understanding may be incomplete. Star formation in the young universe may have been far more efficient than we assumed. Dark matter may have guided structure in ways we have not yet fully grasped. Most researchers believe these tensions will eventually be resolved within the existing framework as early universe astrophysics becomes clearer. Still, unanswered mysteries remain. One of the deepest involves the unseen components of reality itself. Ordinary matter, the atoms that form stars, planets, and people accounts for only about 5% of the universe's total energy content. Roughly 27% appears as dark matter, known only through its gravitational pull. The remaining 68% is dark energy, an enigmatic influence driving the universe's expansion to accelerate. The Big Bang model accommodates these ingredients because observations demand them. But it does not explain what they truly are. Their nature remains hidden. Together, these uncertainties reveal how much is still veiled. They leave room for new ideas to enter. They suggest that while the Big Bang captures something profoundly real about cosmic evolution, it may not be the final word. Perhaps there exists a framework that avoids an initial singularity altogether. One that describes origins without requiring an infinite breakdown of physics. This is where the idea of the Big Bounce emerges. Envision the universe not as a one-time eruption, but as a living rhythm, a cosmic pulse. Expansion follows contraction. Contraction gives way to renewal. In this view, the universe does not begin in an absolute point of collapse. Instead, it tightens, reaches a limit, and then rebounds into a new era of growth. The crunch transforms into a bounce. This cycle may have repeated endlessly without a first moment or a final one. The intuition behind cyclic existence is ancient. Hindu cosmology spoke of vast epochs of creation and dissolution unfolding across unimaginable spans of time. In the West, philosophers like Friedrich Nietzsche reflected on eternal recurrence, though without scientific grounding. What distinguishes modern bounce models is their foundation in mathematics and physical law. The first serious scientific attempt appeared in the 1930s through the work of Richard Tolman. Using Einstein's equations, Tolman explored whether an expanding universe might eventually reverse and contract. His models allowed for repeated cycles of expansion and collapse. However, entropy, the tendency toward disorder, posed a serious challenge. Each cycle grew longer than the last, and tracing them backwards still led to a first contraction ending in a singularity. Even this oscillating cosmos could not escape an ultimate beginning. For decades, such ideas remained in the shadows, while the Big Bang dominated cosmology. That changed near the turn of the 21st century, when new approaches to gravity began to take shape. Among them was loop quantum gravity, an effort to unite gravity with quantum mechanics by rethinking the nature of space itself. In this framework, space is not smooth and continuous. It is granular, composed of tiny, discrete units, more like a woven tapestry than an unbroken surface. At scales around 10 meters, the Planck-length quantum effects of gravity become unavoidable. Physicists Martin Bajauld and Abhay Ashtekar applied these ideas to the early universe and uncovered a striking possibility. When matter is squeezed to extreme densities, quantum gravitational effects generate a repulsive influence. Instead of collapsing endlessly inward, the universe is pushed back outward. The singularity is avoided. Collapse gives way to renewal. In this picture, the universe does not die at its limits. It turns around. and in that turning, it begins again. Rather than collapsing into an impossible point, the universe in these models tightens only to a smallest scale, then turns outward once more. Contraction gives way to renewal. Expansion follows. In this picture, the singularity vanishes entirely. There is no moment where the laws of physics shatter. The mathematics remains intact, guiding a smooth passage from shrinking cosmos to reborn expansion. History does not stop at the rebound, it continues beyond it into an earlier phase that existed before our own. Another powerful vision comes from Roger Penrose. The British mathematician and physicist awarded the Nobel Prize in 2020 for his work on black holes. In the early 2000s, Penrose introduced a framework known as conformal cyclic cosmology. Though distinct from loop quantum cosmology, it shares the same radical intuition. The universe unfolds in cycles rather than emerging from nothing. Penrose begins not at the beginning, but at the very end. He asks, what becomes of an accelerating universe after unimaginable spans of time? Matter decays, stars fade. Black holes swallow what remains, then slowly evaporate through Hawking radiation. Eventually, nothing is left but radiation and empty space, stretching endlessly. And here lies the subtle insight. In a universe without mass, there are no clocks and no rulers. Without matter, distance and duration lose their meaning. Penrose argues that this ultimate future is mathematically indistinguishable from the universe's earliest state. Through a conformal transformation, the end of one cosmic eon flows seamlessly into the birth of the next. What appears to be a beginning is simply a continuation, disguised by a change of perspective. This model dares to make predictions. Cataclysmic events from a previous eons, such as collisions between supermassive black holes, could leave faint. Circular signatures in the cosmic microwave background, Penrose calls these traces Hawking points. He has claimed to identify such patterns, though many cosmologists remain unconvinced, suggesting they may arise from chance rather than deep cosmic memory. String theory opens yet another doorway. In the early 2000s, Paul Steinhardt and Neil Turok proposed the ekpyrotic universe. Drawing on ideas from higher dimensional physics, in their model, our universe exists as a three-dimensional brain embedded in a higher dimensional space. From time to time, this brain collides with another parallel one. Each collision releases immense energy, an event that, from within our universe, looks exactly like a Big Bang. The ekpyrotic picture explains cosmic uniformity without invoking inflation. Before collision, the brains are smooth and flat. That smoothness is transferred into matter and radiation during impact, naturally producing the striking uniformity of the cosmic microwave background. Despite their differences, all these models share a common refusal. They reject the idea of an absolute beginning. The universe does not emerge from nothingness. It transforms. It passes through phases. There is always something prior, another cycle, another contraction, another deeper structure beneath what appears to be an origin. The philosophical weight of this idea is immense, and we will return to it in greater depth later. If time has no first moment, then questions about ultimate creation begin to dissolve. There is no need to summon universes from nothing or appeal to spontaneous beginnings, and new mysteries arise in their place. If the universe rebounds endlessly, was there ever a first rebound? If change stretches backward without limit, how does the mind comprehend such infinity? Endless regression strains our intuition. Entropy presents another challenge. Disorder should increase with every transformation. After infinitely many cycles, shouldn't the universe reach a state of complete equilibrium, where nothing new can happen? Some models suggest entropy may be diluted or reset during each rebound, though the exact mechanism remains uncertain. Still, these ideas are not empty philosophy. They engage real physics and offer testable consequences. Loop quantum cosmology predicts specific signatures in the earliest moments of expansion. Ekpyrotic models forecast polarization patterns in the cosmic microwave background distinct from inflation. Penrose's framework searches for circular imprints from previous eons. These are not metaphors. They are measurable possibilities. And at the heart of all of them lies a single, unsettling insight. Perhaps singularities are not fundamental truths about reality at all, but signs that we are still learning how to listen to the universe's deeper rhythm. These singularities may not be real features of existence at all, but shadows cast by pushing general relativity beyond where it can speak truthfully. Just as Newton's laws failed at extreme speeds and were reshaped by relativity, gravity itself may require a quantum description to remain coherent under extreme conditions. In that deeper framework, collapse does not end in rupture. It turns inward, then outward. Transition replaces a breakdown, which, if any of these ideas is correct, remains unresolved. All such models live at the edge of what we can verify. They extend known physics into realms beyond direct experiment. Yet they are not fantasy. They are mathematically rigorous, scientifically motivated, and in principle open to observational tests. In the next stage of this journey, we will examine what evidence might support these alternatives and how they compare to the formidable observational success of the Big Bang. At first glance, the Big Bounce may sound like speculation wrapped in philosophy. But beneath the surface lies serious theoretical machinery and concrete predictions. While it lacks the overwhelming empirical confirmation that the Big Bang has accumulated, it offers striking conceptual strengths and a handful of suggestive signals. Its greatest appeal lies in its simplicity. These models resolve several long-standing cosmological puzzles without piling on extra assumptions. Consider the horizon problem. In a universe that contracts before it expands, regions now separated by vast distances were once neighbors. During contraction, they had ample time to share information, exchange heat, settle into equilibrium, long before the rebound ignited expansion. No rapid inflationary burst is required. The flatness problem dissolves in a similar way. Across repeated expansions and contractions, curvature naturally smooths out. Any initial bending of space is stretched thinner with each phase. The bounce itself may even demand near flatness as the price of a stable transition. And most crucially, these models erase the singularity altogether. The universe never reaches infinite density. It halts at a finite, though staggeringly high threshold where quantum gravity steps in and reverses the collapse. Loop quantum cosmology gives this idea precise form. Its equations reveal that as matter compresses, the granular structure of space generates an effective repulsion. This force grows rapidly with density and becomes dominant near the Planck scale, around 10 grams per cubic centimeter. At that point, quantum corrections overwhelm classical gravity. Contraction stops, rebound ignites. The resulting expansion resembles inflation in its power, but its origin is different. No mysterious scalar field is required. Quantum geometry itself supplies the push. Numerical simulations confirm that this process is self-consistent. Researchers can track a universe from contraction, through the bounce and into expansion. Using quantum-corrected equations, and the outcome closely mirrors the universe we observe today. Even the delicate patterns of cosmic structure emerge naturally. These simulations show that quantum effects generate nearly scale-invariant density fluctuations, much like those attributed to inflation. But there is a subtle difference. Loop quantum cosmology predicts a slight suppression of fluctuations at the largest scales, because the bounce imposes a minimum wavelength. Intriguingly, traces of this effect may already exist in the data. Measurements from the Planck satellite reveal less power at the largest angular scales than the simplest inflationary models anticipate. This anomaly, known since Cobe first observed it in the 1990s, has long been dismissed by many as statistical noise. Yet some see it as a faint echo of a deeper truth, a universe that did not begin in rupture, but in return.